Hi everyone, I'm Chris and welcome back to the lecture on neural networks of this machine learning course. In this section, we will learn how to train a single layer perceptron. This leads to the famous delta rule. Let's start with reconsidering the single layer perceptron. This neural network takes capital K input variables, x1, x2, up to x capital K. The network processes these independent variables with capital L neurons. Each neuron performs a linear combination of the input variables with parameters w and adds a bias. For the lth neuron, this summation dl is the sum over k of wkl times xk plus w0l. The weight parameters wkl of the lth neuron are multiplicative modifications of the kth input variable. These parameters are represented by the gray arrows. The term w0l is the bias term. Note that the summation can be started with k is equal to 0 instead of 1 to include the bias term. By definition, x0 equals 1, so w0l is integrated into the summation. Each summation is the input of an activation function sigma of zl. Note that sigma can be the sigmoid function or any other activation function as well. Sigma of zl is the output of the lth neuron y tilde l. We need to represent vectors as summations and vice versa. So, here is a short reminder of these relations. A vector z can be decomposed into a summation of vectors along the coordinate axis. This means into a sum where each vector has a single non-vanishing component only. So the vector z with its components z1, z2 up to z capital L is equal to the vector with a single non-vanishing first component z1 plus a vector with a single non-vanishing second component z2 and so on, plus a vector with a single non-vanishing last component z capital L. We can put the z components as scalar in front of the corresponding vector. Then we have z1 times a vector with a single non-vanishing first component 1 plus and so on. As you can see, we have a sum of unit vectors. The lth unit vector is a vector with a single non-vanishing lth component 1. So the vector z is written as sum z1 times unit vector e1 plus z2 times unit vector e2 plus and so on. In short form, this is vector z equals the sum over all components L of dl times the unit vector el. So we can replace a vector by the sum over its components times the corresponding unit vector. A similar representation is obtained for a gradient. A gradient is the derivative of a function like the cost function h with respect to several variables or parameters w1, w2 up to w capital L. These parameters can be expressed as a vector w. The gradient is a row vector by definition. The definition of the gradient of a function h with respect to the parameter vector w is the derivative of h with respect to the parameter vector's first component w1 their derivative of h with respect to w2, and so on. This can be decomposed into a sum of row vectors with a single non-vanishing component only. So the first row vector has a non-vanishing first component, the partial derivative of h with respect to w1. The second row vector has a non-vanishing second component only, and so on. We can put the component value in front of the corresponding row vector. This is a sum of components times the corresponding row unit vectors. The else unit vector transposed is a row vector. It has a single non-vanishing component 1 at the else position. So the gradient of h with respect to the vector w is equal to the sum over all components L of the partial derivative of h with respect to the else parameter wl times the else row unit vector EL transpose. So a gradient in its vector notation can be replaced by the sum over its components times a row unit vector. As reminder, if the vector is in the denominator, we need a transposed unit vector for the decomposition. Let us quickly come back to the single layer perceptron. The capital L summations VL can be expressed by a vector z. Every component of this vector corresponds to the summation v of one of the neurons. As we've seen, we can represent the vector v by a summation over all components L of dl times the corresponding unit vector EL. If we substitute the expression for the component ZL into this representation, the vector z is the sum over all vector components L and the sum over all input variables k of the weight wkl times the input xk times the unit vector EL. Note that for k is equal to 0, we have the bias parameter w0l. The output vector y tilde is equal to the vector z if the activation function sigma is applied to every component. So we write the vector y tilde as sigma of vector z. But we keep in mind that the activation function is applied component by component. We need to specify a cost function in order to fit the neural network with its parameters to data. The cost function measures the quality of the model fit to the training data. The weight parameters are varied to minimize the cost function. Here we choose a mean squared error cost function h and consider a single data point x, y. This represents a stochastic gradient descent approach. We will learn about this later. However, it is straightforward to take also more data points into account. You just need to incorporate a sum over all data points by I. So, for a single data point, the cost function h is 1/2 times the sum over all output components indexed by L of the square difference of the else output component y tilde L and the corresponding true target value of the data point YL. So, how do the weight parameters of the neural network need to be adjusted with respect to the data point XL? We can use a steepest descent minimization of the cost function h. Starting from initial values of the weights wkl, the weights are varied along the direction of the gradient of the cost function. This is because the gradient is perpendicular to the lines of constant height, the contour lines. Further, the gradient points in direction of steepest ascent, or with a minus sign along the direction of steepest descent. So the minimization tries to find a new location in parameter space with a smaller value of the cost function. The step size eta is a fixed value which determines how far to go into the direction of steepest descent. If you want to learn more about this, please take a look on the section of model training. For a specific weight parameter WKL, the update delta WKL is equal to minus eta times the related component of the gradient, which is the derivative of h with respect to WKL. We need to calculate the gradient of the cost function for the parameter updates. We need to calculate them in an efficient way because we usually can have a high-dimensional parameter space. This is because a neural network can have a lot of weights. The cost function depends directly on the output variables y tilde l. The output variables are the activation functions of the corresponding summations. And the summations depend on the trainable parameters w. So we can express our component of the gradient of the cost function with chain rule. The derivative of the cost function h with respect to the parameter WKL is the derivative of the cost function with respect to the neural network's output vector y tilde times the derivative of this vector with respect to the summation vector d. And this times the derivative of this vector to the parameter WKL. We need to calculate all of these three contributions. Using a sigmoid activation function for sigma gives for the weight update delta WKL equals minus eta times the difference of model output and data y tilde minus y times the model output y tilde times 1 minus the model output y tilde times xk. So the weight update is expressed just in terms of the data and the model output for all weight parameters. For a linear activation function we have delta WKL equals to minus eta times the difference of model output and data times the cased input variable. This is called the delta rule to update the weights of a single layer perceptron for a given data point. We will derive these results for the weight parameter update by calculating the gradient of the cost function step by step. Let's start by calculating the last of the three contributions to the gradient according to chain rule. This is the derivative of vector z with respect to the weight WKL. The summation vector z is the sum over all output components by L prime and the sum over all input variables by K prime including the bias of WK prime L prime times xk prime times the unit vector EL prime. The derivative is now straightforward to calculate. Note that we used L prime and K prime as summation indices, so we can place the derivative into the sum. The derivative of this expression with respect to WKL has a non-vanishing contribution only if K prime equals K and L prime equals L. So both summations collapse and the derivative of WKL times xk times the unit vector EL with respect to WKL remain. the derivative of WKL with respect to WKL is 1. So the summation for the derivative of the summation vector z with respect to a parameter WKL is xk times the unit vector EL. The second contribution to the gradient according to chain rule is the derivative of the output vector y tilde with respect to the summation vector z. This gives a matrix. As shown before with the summation vector, the vector y tilde can be expressed as sum of all of its components multiplied with a corresponding unit vector. This can be substituted for y tilde in the derivative. The gradient can be decomposed into a sum of its components as well. Thereby, the gradient is the sum of all of its components times the corresponding transposed unit vector. Note that we have to use different summation indices to mix the sums. So we place the summations in front and the unit vectors at the end. This gives the sum over L and L prime of the partial derivative of y tilde L with respect to dl prime times the unit vector EL times the transposed unit vector EL prime. The product of the two unit vectors is displayed below. It is calculated with the rules of matrix vector multiplication. So row times column. Here, this means the first component of the first vector as a row is multiplied with the first column of the second vector, which has only a single component as well. This gives the first entry of the resulting matrix, which is 0 here. Now we take a closer look on the matrix components. To calculate the corresponding derivative, we need to specify the activation function. Here we choose the sigmoid activation, but you can perform the following calculations with any other activation function as well. So the output y tilde L is the sigmoid function taking the summation dl as input. We have y tilde L equals 1 over 1 plus exponential function of minus dl. This can be written as 1 plus exponential function of minus dl to the power of minus 1. This notation simplifies calculating the derivative. Now we substitute this expression for y tilde L into our derivative of y tilde L with respect to dl prime. The derivative of an expression depending on the variable dl with respect to the variable dl prime is only non-zero if the variables dl and dl prime are identical. So for example, the derivative of an expression with the variable d1 with respect to d2 is always 0. Consequently, only L equals L prime gives a non-vanishing result. This can be expressed by the so-called Kronecker delta, delta LL prime, which gives a 1 for equal indices and a 0 otherwise. So we can replace L prime by L if we multiply our derivative with a Kronecker delta. Calculating the derivative of our expression on the top, the exponent is subtracted by 1. This gives the denominator 1 plus exponential function squared and a minus sign. The derivative of the inside is the derivative of the exponential function of negative dl. So the numerator is the exponential function with a minus sign. This minus sign cancels with the minus sign from the negative exponent. Note that the Kronecker delta is a constant with respect to the L, so it stays untouched. Next, the result is splitted into two factors by splitting the denominator into its factors. Further, in the term on the right in the brackets, in the numerator we add and subtract a 1, here marked in blue. This gives us the chance to split this factor into two summands. The first one takes the plus 1 and the exponential function of the numerator. Here, the numerator and denominator cancel each other, which gives 1. The remaining minus 1 of the numerator gives minus 1 over 1 plus exponential function of minus the L. When we take a look on the definition of the sigmoid function, we can substitute the first factor by this function, which is nothing else but our output y tilde L. Further, the term in the brackets is 1 minus y tilde L. So the derivative of the Lth component with respect to the L prime summation is y tilde L times 1 minus y tilde L times the Kronecker delta L L prime. The second term of the derivative of vector y tilde with respect to vector z was expressed by the sum over all components L prime and L of the derivative of y tilde L with respect to the L times the Lth unit vector times the L prime's unit vector transposed. The derivative was calculated using the sigmoid activation function, which gives y tilde L times 1 minus y tilde L times the Kronecker delta L L prime. We can put everything together, which gives the sum over L and L prime of y tilde L times 1 minus y tilde L times the Kronecker delta L L prime times the unit vector EL times the unit vector EL prime transpose. The two summations consider all possible combinations of L and L prime. However, because of the Kronecker delta, there is a non-zero contribution only if L equals L prime. So the two summations collapse into a single one, and here we choose L as summation index. This gives the sum over L of y tilde L times 1 minus y tilde times the unit vector EL times the unit vector EL transpose. Finally, we considered the derivative of the cost function h with respect to the output vector y tilde. The cost function was chosen to be the mean squared error of all components. So h equals 1/2 times the sum over all output components by L of the squared difference of model output y tilde L and data's true value YL. The gradient with respect to the vector y tilde is expressed by the sum over all components L prime of the derivative times the unit vector EL prime transpose. The vector is transposed to represent the row vector of the gradient. The derivative of the squared difference is 2 times this difference. The factor 2 cancels with the factor 1/2. So we have the sum over L prime and L of y tilde L minus YL times the Kronecker delta LL prime times the unit vector EL prime transpose. The two summations reduces to a single one due to the Kronecker delta LL prime. This gives the sum over L of y tilde L minus YL times the unit vector EL transpose. Now we can put all three contributions to the cost function derivative according to chain rule together. If we substitute these three expressions into the formula for the weight update delta WKL, we have the expression shown here. Note that we used L' and L double prime so that we can mix the factors in both summations. If we take a look on the multiplication of the unit vectors, we see that they reduced the summations. The unit vector EL' transpose times the unit vector EL double prime is calculated according to the rules of matrix vector multiplication. So row times column. The first transposed unit vector, a row vector, has a 1 in the L' component and zeros in all other components. The second unit vector, a column vector, has a 1 in the L double component and zeros elsewhere. The product is only non-zero if L' equals L double prime. So the product is equal to the Kronecker delta L' L double prime. Similarly, the product of unit vector EL double prime transpose times unit vector EL gives a Kronecker delta L double prime L. Consequently, both Kronecker deltas require L' equals L double prime equals L to give a non-zero contribution. So finally, our weight parameter update for WKL of a single layer perceptron with sigmoid activation is minus eta times y tilde L minus YL times y tilde L times 1 minus y tilde L times xk. This expression is called the delta rule for sigmoid activation. Often, the middle term is abbreviated by delta L sig for sigmoid, not to be confused by the Kronecker delta. For a linear activation, this reduces to delta WKL equals minus eta times the difference of the model output y tilde L and the true data value YL times xk, the cased input variable. The difference vector can be abbreviated by delta L lin for linear activation. This is the delta rule for linear activation to update weights in a single layer perceptron for a data point. As said, we can generalize this to incorporate more data points by summation over all data points. Section finished. Thank you very much for listening. If you liked this video, please click the like button and consider to subscribe this channel. If you have any comments or questions, please leave a comment down below. And thanks again for listening. See you in the next section.